We, that is the ASI, the Austrian Standards International, formerly called the, oder das Österreichische Normungsinstitut, maybe some of you know this by this name, and the University of Applied Sciences, Upper Austria. ISO, that's the International Standardization Organization, and WG21, that's the working group within the ISO that standardizes the C++ programming language. By the way, this working group currently consists of, say, 400 to 500 delegates of their national bodies. These delegates are all proven experts in the C++ programming language, and we have two outstanding representatives of them here today as speakers. Jens Maurer and Sutter. It's by no means a matter of course to have them here. Because in a week in which WG21 meets, intensive work is carried out every day, from early in the morning until late in the evening. Those of you who attend here as guests will confirm this. And now I have to apologize to the audience. Like me, you will also miss the third speaker announced for today. The creator, mentor, and some say father of C++, Björn Strostrup. Jan has kindly agreed to give an invited talk in advance, but unfortunately, he was unable to come to Hagenberg. I'm so sorry for this. So now let's turn to the first speaker for today, Jens Maurer. Jens is the so-called logistics officer of the WG21. In this function, he's a great help to the hosts in organizing a meeting and therefore also for us. Thank you very much for all your help, Jens. Jens has another important role in the WG21. He's the chairman of the Core Language Wording Group, which deals with the wording and consistency of the core language in the standard. In his talk, Jens will explain to us how ISO and WG21 work. Please give a big hand for Jens.
All right, so yeah, that seems to work microphone-wise. So, welcome everybody from me. My name is Jens Maurer. I'm from Germany. So supposedly I could do this in German, obviously, but Peter said it's all English here, so let's do English. I studied computer science in Kaiserslautern in Germany, in the western part of Germany, and I'm now working for a company processing financial data, eventually owned by an American company, but of course I'm working for the German subsidiary of them due to various interesting tax and employment law and whatnot reasons. All right, today I'm talking a little bit about what the group that is meeting here this week actually does and how it fits into the picture. That is more organization, administration kind of things. If you want to hear about actually C++ topics, as in technical language topics, you have to sleep for about 15 minutes until it's Herb's time. All right, so the name of the group that's meeting here is ISO/IEC JTC1 SC22 WG21. All right, lots of acronyms here. Let's have a look at the acronyms. And that probably explains a little bit what the context is of this group. So ISO stands for International Organization for Standardization. Now, if you look at the capital letters there, and if you compare them with the capital letters in the word ISO, you might discover that the order is a little bit off. The reason has multiple ones. The first is ISO means equal in Greek, so it's kind of nice to be spelled ISO. The other reason is that if you translate the name International Organization for Standardization in other languages, in particular into French, you find out that the letters switch order. That's the same with the acronym for NATO, North Atlantic Treaty Organization. If you translate that to French, then it's Organisation pour la Traité de l'Atlantique du Nord, or something like that, and it's OTAN as an acronym. And if you watch TV, and sometimes you see both of those acronyms, NATO and OTAN, above each other, but that means it's sort of not recognizable if you just see one of the acronyms and not both. So in short, not satisfying any particular order in any particular language and just randomly arranging the letters to read ISO is dissatisfies everybody, so it's a good solution. So next is IEC, that's the International Electrotechnical Commission. That's an international standardization thing for anything that runs with electricity. So, and ISO is a federation of national standardization bodies. Peter talked about ASI, the Austrian national standardization body. In Germany, it's called DIN, Deutsches Institut für Normung. In France, it's called AFNOR, Association Française pour la Normalisation. I guess, I don't know what it actually means. And so on, and those got together and said, gee, national standards are great, but wouldn't it be great if we could sell our goods and services across borders? And so we should have international standards, not just national ones. So at the heart, ISO is just a collection and a federation of those national bodies, and nothing happens in ISO without consent of those national bodies. All right, at some point, someone discovered there's computers out there, so they figured we should maybe standardize something in the field of computers. And then someone discovered that computers run on electricity, so it was somewhat related to the electricity people in the IEC. So the end result was they actually got together as opposed to competing and formed JTC1, the Joint Technical Committee 1, whose topic is doing everything that involves information technology. Those people got together and figured, gee, information technology is sort of a large topic. Let's subdivide this a little bit. And they formed a number of subcommittees, among them Subcommittee 22, which does programming languages, system interfaces, and something else I forgot. So, and they got together and said, gee, that's sort of a large topic here, all those programming languages. I know at least 5, so maybe we should subdivide this a little bit. And then they formed working groups, one for each programming language. And the working group for C++ is WG21. So that's why the group that's meeting here has this interesting long name, because it's just the hierarchy, the path and the hierarchy tree of the organization that is described by that. All right. So there we are. A few figures. What are we doing here? In general, our group meets 3 times per year. Plus, we do have teleconferences. We started having teleconferences in earnest when COVID hit. and we never could stop afterwards, unfortunately, even though we resumed in-person meetings. So yeah, so that's what we have. So this is one of the meetings we're having in the year 2025. We will be in Sofia, Bulgaria in summer, and in November we're going to be in Kona, Hawaii, at the other end of this planet, which is sort of inconvenient travel-wise. All right. Supposedly we're about 120 people here. I think someone counted recently and it's actually 140. So okay, whatever. We have about 60 people remote. We try to enable remote attendance for all our sessions here. So all our meeting rooms are equipped with remote attendance gear. In this location, we actually have a lot of gear already in place. As you can see, I have a university-owned microphone in my hand. We have cameras and all that. That's very nice here. In other places, it's sort of less nice. And sometimes when you are in hotels, in particular in US hotels, they like to charge you quite a bit for just using a projector and a screen. And that actually is much more expensive than just buying a projector and hypothetically thrown away at the end of the week. So yeah. Anyway, national bodies, we have more than 20 participating in C++ standardization. Not all of them are present at all times, but they certainly follow what we do, and they are occasionally asked, as in a 3-year cycle, they are asked whether they consider it okay what we're doing here, and they can submit formal comments of what we want to publish, or about what we want to publish. So we're lots of people, as you can see. If you consider everybody in this room here, and then you want to have some workshop-style atmosphere where you can criticize suggestions for changes to the C++ programming language, that does not work, because 300 people times everybody saying something for 5 minutes, and the week is over. So we divide up in subgroups, and we have 7 parallel sessions during this week, where several subgroups meet in parallel. Some subgroups meet all week. Some subgroups just meet 1 or 2 days, or even an afternoon during this week. Our tracking system for what's called papers currently has about 400 open papers. Again, those papers are not academic papers, as you might be familiar with, but those are essentially suggestions for changes to the C++ programming language, with rationale why that should be done, why that is a good idea, why things can be done much better, and so on. The end result of our efforts is the next revision of the standard for C++. We call the ongoing small increments we use for our daily work, we call those things working drafts. And every 3 years we make a snapshot and publish that snapshot as the next standard, after consulting with the national bodies, which usually give us a long list of comments of things. You would hope that the people writing those comments inside the national bodies actually are those that attend the meetings. Sometimes that is the case, sometimes it is not. All right, so currently we have 2,400 pages of working draft, of which 500 pages describe the core language and 1,600 pages describe the library. If you believe my math is off because I can't sum, yes, there is also a table of contents, there's an index, or several of those, there is a list of changes relative to older standards, and so on, so that's the remainder that makes up for the difference. All right. Now, we're plenty of separate subgroups, and yes, this picture was stolen from the public website we maintain, and that picture was probably made by Herb, so Herb, I hope that's okay for me showing that here. And so, as you can see, we have an interesting matrix of subgroups here. The green, yellowish things here are what's called study groups. Those are mostly domain experts. So, for example, anything involving Unicode, involving text transformations would go to SG16 text first before it would go anywhere else. That study group would make sure that the topic relating to text is adequately described in that change suggestion. It would make recommendations how to improve the paper, and then once that study group thinks everything is nice and shiny, that paper would go, or a revision of the original paper, of course, because changes have been made, would go to the next stage, which are the evolution working groups. We have one that deals with the core language and one evolution group that deals with the library. And those would decide whether it is actually desirable to have that change, and whether there's overarching concerns that need to be addressed. Yeah, and that's usually where the interesting discussions happen, because not everybody is of the same opinion on what the shape of future C++ should be. And we've had some of that this week, of course. So once the evolution working groups are actually happy, the next stage is that the paper goes to the wording review working groups, which is again one for core and one for library. So at that point, we expect the proposal to have a section of text in it that actually describes changes to the working draft. So it's not any descriptions anymore, what would be nice to have or so. It's actually instructions how to change the current working draft to achieve what the paper wants to achieve. And at that point, those wording review groups actually check that the text in the paper does that, doesn't do harm to the rest of the standard, because accidentally doing bad things, and generally makes sure it's of the right shape, also makes sure there's enough commas in there and whatnot. After that, we go to the full plenary that is going to happen on Saturday morning, and on Saturday morning we get together in this room, and we will have a list of papers that we will approve here, hopefully, and that's essentially the last meaningful chance where someone can say, oh, no, I don't really want this. We expect all technical concerns to have been brought forward earlier than the plenary, but still we want to make sure everybody's on the same page. Yeah, then the editors update the working draft for the next meeting, and the cycle repeats. Occasionally, as I said, every 3 years, we make a snapshot of that and push it up onto the gray area up there where it says SC22, and the national bodies constituting SC22 will then comment on that snapshot in a formal process. Takes about a year until we finally get up to JTC1 there. They also need to approve, and then there's one box missing. I would designated by a red circle or something, which is ISO Central Secretariat in Geneva, which then gets what we would like to publish as the next standard, as an official standard. They read through it and say, yeah, we are the editors, the technical editors of ISO, and we tell you that you cannot use certain words in notes because that's not allowed. We tell you that your pagination is off and doesn't look nice. And sometimes they tell you, oh, that's nice. You have 2,400 pages here. Could you just restructure it completely and do whatever. Never mind that the paper, that the C++ standard is, of course, now whatever 27 years old. The first revision was published in '98. So yeah. Depending on the situation and the current people that you deal with there, that takes longer than expected. Anyway, all right, so that's that. Yeah, I guess the 15 minutes are over, so I need to stop here. Any questions?
So, thank you, Jens. We have time for some few questions. Your questions, please. And I think we should take a mic.
What does the 21 mean? Is it start here? What's the 21 in the name?
Oh, it's just an ordinal number. We're just the 21st working group that got instantiated in SC22. And the 22 in SC22 means it just happened to be the 22nd subcommittee that was devised. And the JTC1 means, oh, that's actually the first joint technical committee between those two organizations. There isn't a second one as far as I understand. So, so, for example, the C programming language is WG14 because they were slightly earlier. And then we have Ada and Fortran that even get slower numbers because those were even earlier.
And C came from B. I said, and C came from B.
B doesn't have an ISO committee.
I have another question here. So you're doing a lot of work for the C++ standard. So who is paying for the time that you need to?
My wife, essentially, or so. I mean, don't go to the movies. Do something useful.
No, they gave me a mic. So just to expand on that, so people come representing companies, and so their companies may send them. They may be consultants or teachers or article authors who make a living on C++, and so they may come here to be informed or to influence things. They may be individual people who are interested, who maybe work in tech, but their companies won't send them, so they take their vacation time and buy plane tickets and pay hotel out of their pocket to be here. Nobody gets paid to come here unless you're working for a company that sends you. It's all volunteers.
So when I started this, it was vacation time for me, and it has slowly evolved into actually fully paid business trip right this moment, including getting business class flight on flights of more than 10 hours.
Okay, then thank you, Jens. And now let's turn to the second speaker for today, Herb Sutter. One could now list all the books and articles Herb has written, all the talks at major conferences he has given, all the interviews, all the papers for WG21, etc., etc. That would be a quite long list. I would just like to highlight one paper that was important to me personally. The free lunch is over. And this paper is not necessarily about C++. In addition to all these things, Herb has another important role. He's also the so-called convener of the WG21. As such, he is simply the boss of the whole thing.
I get to organize when and where meetings happen, and occasionally people listen to me a little bit, but otherwise I'm just another participant. I organize when and where the meetings happen. That's what a convener does.
In his talk, Herb will give us a glimpse of how to use things, of how things will continue with C++. Please give a big hand for Herb Sutter.
So I promise that the slides in the talk will be in English. Aber erstens mal, Peter, wiedermals vielen Dank zur Universität, Softwarepark Hagenberg und alle, die gekommen sind. Wollen wir den Peter und der Universität bitte vielen Dank geben? Danke, dass wir hier arbeiten können diese Woche. We're able to have an incredibly productive meeting thanks to the University, Software Park Hagenberg, and we appreciate that. We have a lot of interesting, exciting things happening in C++, and I get to tell you about some of them. So I will try to point out where some things are just my personal opinion. I organize the committee only to the extent that of saying when and where meetings will be. Anything else is gravy if they ever listen to me on something. But I am excited about C++ as a user and as a programmer of C++ because I think we're at a turning point for C++ that, to me, and again, this is just my personal opinion, is on the order of the turning point that we've hit once before with C++ 11. So how many of you have heard the term modern C++? All right. Now, as soon as you ship ask Andrei Alexandrescu, as soon as you ship a book that says modern C++, and 5 years later, the way you program is different, and so modern is a shifting thing, right? It's like, oh, what is modern? But it's actually stuck very well for C++. Because C++ 11 was a watershed release. Bjarne Stroustrup correctly called it feels like a new programming language. There was enough different, even though it was fully backward compatible. All of your old C++ code largely worked with very few exceptions. But we now had auto type deduction, we had lambdas, we had range-based for loops, like other languages. We had standard smart pointers, you didn't have to go to Boost or roll your own. We had lambda functions and other things that we never had before in the standard, so that if you to this day, you open up a piece of code and you look at it, you can tell whether it was written before or after C++ 11. Like to this day. And yes, since then we've done other exciting things. I'm not saying that concepts in C++ 20 weren't great. Modules were great, coroutines, generic lambdas, because we got lambdas in 11, but then it was 3 years later before we got generic lambdas and reduced return types and parameters, that kind of thing. Those were all great too, but they were in some sense an icing. They were of the same era, where you could open a file and immediately see this is in the C++ 11 era, and so we kept making it better. We finished C++ 11 with things like generic lambdas, and then we kept making it better. But it didn't fundamentally, nothing we've added since 11 has fundamentally changed our programming style in a way that you could see in any random 10 lines of code. C++ 11 did. Any random 10 lines of code, you can tell whether it's modern or not. And I think we're getting to a place where we are now at the beginning of an era where you'll be able to, with C++ 26 and the following standards, so just beginning in C++ 26, the initial parts, to actually change the way we write our code because of safety by default and because of reflection. And both of those are going to take much more work than we can do in C++ 26. But let me talk about those two things. First, reflection and why I think it's important. And I'll give a little example. There's only time for a little example, but hopefully to give you a sense of how these things work and why they're impactful. About safety, specifically talking about programming language safety. And then I want to talk a little bit about simplicity, how both of these things can make our C++ code simpler, can make our C++ tools, our environments that we use simpler. And just so I get a show of hands, so I know who I'm talking to, how many of you are students here at the university? Can I see the hands? Lots, okay, I'm not surprised. How many of you have worked or currently work in industry using C++? So it's about half and half. So the reason I ask is because when in that third section, I talk about things like tooling, I'm going to talk about things like, oh, here's your C++ compiler, but here's these other tools you use. Maybe it's a mock compiler. Maybe you spit out idle output on Windows. Those are all parts of what it takes to use C++, where the compiler is just one part. It's the language, we love it. It's an essential part that we use, but it's just one part of the complex structure of the software we use to build programs and to ship programs, to test them, to deploy them. And you might be more familiar with that if you've been in industry and seen what it takes to actually ship software. Whereas if we're in academe and we've mostly just used the programming language for school assignments, generally we get to, most of the time, say, oh, I write my source code, I compile it, and I run it. And that is such a beautiful, simple world. And I wish the real world stayed that way. But I think both of these features will get us a step closer to that world, to simplify not just the code, but the tooling that we use. And so that's just a bit of a flavor for what to expect. Normally in a talk, I pick one theme. So why am I talking about two very different things, apparently, reflection and safety, in the same talk? Well, in part because they're related. I think both of these things there are other things that are happening in C++ 26 that are important. Looks like we might get contracts this week, or pre and post conditions in the language for the first time, things like that. Those are important too. But both of these are going to change fundamentally the way we write our code. And other things might too, contracts may as well, but I want to highlight these. So they're both, hopefully, fingers crossed, starting in C++ 26. Reflection we might get by the June meeting, which is the deadline. But they're technically related. I'm going to talk about how they're both about reducing undefined behavior. And they're both, in the third part we'll see, will help us simplify the way we use C++. But let's start with reflection. How many of you have used reflection in like Java or other languages? Yeah, so if you're not familiar with what reflection is, it's like looking in a mirror and seeing what's there, seeing yourself. So reflection is the program can see itself. You know how you write a range for loop over like a container? You say for each element in the container. That's just runtime data. Reflection means now I can also say for each member function of this class. And you might first think, well, that's a small thing. And then you realize, oh, I've never been able to do anything like that before. You mean I can actually treat my program as data? Yeah, and wait for it, then also generate new program constructs. Like you can reflect on a class and generate a new one that's just like it, but with a different name, or with a few extra member functions, or things like that, or check things about it. I'll get into other examples. And because this programming is done at compile time, and the program looking at itself and generating more of itself, that is meta. That's what meta means. Meta is like doing thing of yourself. It's like another level up. So this is meta programming, seeing and generating itself. And one difference, if you've seen this in other languages, like some of you raised your hands, what's different in C++ is we care a lot about not incurring any runtime overhead, and we largely stick to this, that you can't opt out of and control, the zero overhead principle. So reflection is entirely at compile time. If you have used Java runtime reflection, you probably know that it's got a reputation of being sluggish. I won't say slow, but sluggish. For example, if in Java you do a virtual method call directly, just write the code in Java, and you do that, and you time it, and then you do the same virtual method call by reflecting on the method and then using the reflection, because Java does runtime reflection, that's something like 3 to 5 times slower. Still super powerful. Still enables libraries and frameworks that you couldn't write otherwise. I mean, Java folks love their reflection. That is not a diss of Java. It's just in Java, the culture in Java is to do things at runtime, to emphasize programmer convenience and do work at runtime. In C++, the culture is you don't pay for it unless you use it. And we do work at compile time. So We're going to try to make sure this doesn't slow down your compile times needlessly. But it means you have zero runtime overhead. Unless you compute some value at compile time and save it to runtime and use it then, you can do that, and then you pay for the storage and stuff. This is not in itself new. The way to think of it is that there has been this 30-year arc where people have noticed that we can do more and more computation at compile time in C++ programs, and we've added more and more support, especially since the C++11 standard, to do it in C++ code itself, so that C++ is its own compile time meta language. And at this point, nearly all of the language is available at compile time. You know, you still can't do std thread at compile time, but HANA is working on it. You still can't do coroutines at compile time, but there are people who are working on it. But most of the language is available at compile time, including dynamic containers. You can new and delete at compile time. And what can you do with these compile time programs now that we have the support for what's called const-expr or const-eval programming? That's the code that's now going to look at the code itself that's going to use the reflections at compile time and do interesting things. So by the way, all of these paper numbers, if you really care to read the papers, I almost want to say I dare you. I should have put this on the slide, but where you can find all these p-numbered papers I talk about, just go to WG21, you've heard of WG21, WG21.link/paper number, and you'll get the latest version of that paper. So WG21.link/paper number. So the very first one gives us basic reflection. We hope this one will make C++ 26, but there are also other additional reflections being proposed. This is the beginning. There will be more in C++ 29 and so on. And also, above the dotted line, not just reading metadata, the program's data state and structure, but being able to create more of it, to generate C++ code at compile time so the program can extend itself in mechanical ways, mostly to automate things so you don't have to do them by hand anymore. Less copy-paste programming. By the way, what's a major benefit of letting reflection and like a compile time program that you wrote, maybe it's 20 lines long or 100 lines long, generate the code for you so you don't have to write it by hand? Well, first, you can test and debug the compile time program because it's code too. This is a big deal. And once you've done that, you run it, you know it's right. Fewer errors. So there are real benefits to doing it this way. Here's a simple example that actually fits on a couple of slides. So thanks to Matush. Let's say that you have a command line parser. So here, let's see if I can find a way to point on the screen so that you can see also in the recording. So if you have compile time options here, and we've probably all had a compile time options library, you know, on the command line, you might say -- count equals this and so forth to give input on the command line. And I realize I could be talking about pay telephones and but we still sometimes use command lines, right? This isn't like pay telephones where I have to explain what it is first. Okay. When you get to a certain age. But so far that actually looks pretty similar to what we're used to. We say we call parse options with, here's the option struct I want to fill in at runtime, but it describes what the options are. And I just pass it my command line arguments, so argv and argc, which is what we get from in C and C++ on the main function. However, you might notice that the way I specify my options is as ordinary data members. I did not call parse options down there with open paren int, comma, string name, comma, that kind of thing. I just wrote the struct with the data members that I want to get populated, that are the command line arguments. Notice I even use conveniences like default values for those data members, another thing C++11 gave us. And one of the benefits we get from that is now if we look in the parse options function, notice as usual, it's templated based on the options that we have. But in this case, we take the type itself, its structure, is part of the input to the function. Why? Because the next thing we do is we have this new for loop that we've never had before that I was talking about earlier that says, I'm not going range 4 over every element of the vector. I'm going for every non-static data member of, so for every member variable. Look at the member variable, and then I'm going to use the standard library algorithm at compile time to match, to see, is the command line argument dash dash that member's name? If so, I'll go and I'll try to convert it to that type. So I'll splice in the name of that data member as if I had written code. This is just a little bit of generation. So that funky square bracket colon syntax means paste in that name here as if I had written it as a normal, dot count variable name. And now this is type safe at runtime. So that splice happens at compile time. Think about when this is happening. It's at compile time as if I had written that dot member name. But the whole loop runs at runtime and takes the actual input the user provided of the command line string, tries to convert it to that type, the correct type for that particular member of the option struct. And if that doesn't succeed, it can say, hey, that's not a valid that type. And so, for example, it can say, that's not a valid int. And here's an example of how that can look. So if you actually run this on Godbolt, you can actually run that code in the prototypes that are available online. There's a site, godbolt.org, that hosts many compilers, including 2 prototypes of this reflection proposal. The Clang-based one, the experimental P2996, if you pass the command line arguments dash dash count 42, dash dash file name, Scott Meyer's Effective Modern C++, because everybody should read that book, then the program prints out opts.file. That file member, which is a std string, has value, Scott Meyer's Effective Modern C++. And the opts.count, which is of type int, has the value 42. This is completely type safe, but you'll see how I'm using the ability just a little bit as a baby step to see the structure of the data at compile time to pass a type, including its structure as input that the function can use, and how that makes things convenient. And this is type safe because if I try to mix it up, if I pass the wrong type, like count is supposed to take an int, right? So what if I say dash dash count Scott Meyer's Effective Modern C++? Well, that's a string, that's not an integer. So I get the error message, hey, sorry, count is not a valid int at runtime, so this is totally type safe. And that's where we want to be. There are many more examples, including a more advanced compile time parser that would take more slides in paper P2996. But this gives you a sense for the kinds of things that you can be able to do. Just a little taste. This is the tiniest little taste. Should I tell you more about the little taste? Okay, here's just, I don't have a slide for this, but just a very, very small taste. Imagine you write a meta function that reflects over a class. So what can it see? Everything, eventually. We have a subset of everything in the first version of reflection, but we'll add to it. Eventually everything. It can see its name. It can see its base classes. It can see its data members, its public API, its virtual API. So if your meta function wants to, for this ordinary C++ type, for just example, at compile time, open a file that has the same name as that class name, .java, and start spitting out a Java code that has a function that wraps a pointer to this type and has a function for every member of the type for the parameters that are convertible. You start to see the possibilities of what you can do. Oh, you want to build a Rust-compatible API? Expose this to Rust. Those are the kinds of things that become possible. And that's why I'm saying this is the beginning of a 10-year arc, because we're going to be spending the next 10 years not just completing the reflection feature in the standard, because we're only going to give you a little bit in the first standard if we succeed, fingers crossed, right? There's more coming. But it'll also take us as a community, as a world, it's going to take us a decade to learn all the cool things we can do with it. Like, this is unleashing power that we have never had in C++ to be able to write programs that were either very difficult before or were impossible before. Now let's talk about safety. Let's shift gears. But I'll show you how these things are related even before we get to part 3. So there's a longer essay there that I published almost a year ago. There's the link at the bottom. And it is a fact that we care about programming language safety. Safety is an overloaded term, and here I'm talking about programming language safety. We care about it for lots of reasons. I mean, if you are writing in a type-safe language, you are already getting many rules enforced at compile time so that if your program compiles, it is free of these classes of errors. By the way, it used to be that people said, if my program compiles, it's correct. And then they realized that, you can write bugs in any language. So if you hear people say that, just smile and nod and correct it in your brain. You don't need to correct them. But it doesn't mean you have no bugs. But it does mean that if the language gives you certain guarantees in memory-safe languages, it does mean you are free of certain kinds, certain classes of errors, at least in most cases, the cases the language rules cover. Languages like C#, Java, Go, Rust, Python have more of those than C and C++ do, especially C. So when it comes to why we care about programming language safety, I want to say both why it's important, but also a few words about why this isn't the whole story either. So programming language safety is important because our software is under attack. If you are working in industry today, whatever code you are writing is either under attack right now, or it will be under attack if it's at all available over a network, if it's useful enough that there's enough instances of it that somebody might write a virus that targets it. Certain countries and certain criminal organizations are real good at this and real well funded to do that, to take advantage of your software. One thing they exploit is type and memory safety. So that's why I use this picture, but it's only one of the tanks that has its barrel aimed at your software's head. Pardon the violent metaphor, but it's like, this is existential. So we want to make sure that that gets pointed somewhere else, that we protect ourselves against that category of attacks. So I'm going to talk about things we're doing in C++ that go way beyond what you can get, the safety you can get in C, that gets us to roughly parity with other modern programming languages in terms of memory safety. But I want to point out, I'm going to talk about that for the rest of the talk, but I want you not to forget all those other tanks. How many of you have heard of MITRE.org, M-I-T-R-E.org? A couple. Okay, so they are one of several important security organizations. They track vulnerabilities, exploited vulnerabilities. They assign them severities. They bucket them into root causes and kinds of attack. So every year they publish, and this is kind of in some cases subjective because they're humans too voting, right? But they publish a MITRE Top 25 CWE, Common Weaknesses list. Then you sometimes hear CVEs, Common Vulnerabilities, but that's a different kind of number. It's sort of more fine-grained. But Common Weaknesses is sort of a bucket of what kind of problem is this? And it might be out-of-bounds read. It might be using a dangling pointer, right? So if you look at the top 25 in MITRE's list, quite a few are programming language safety issues that are in the top 25 things being exploited by evil people. There are bad people who are trying to break your code in order to steal data, compromise your systems, mine Bitcoin. For heaven's sake, if I'm going to get taken over by a virus, I hope it's one that just wants to use my processor for Bitcoin. Is that worth anything anymore? Anyway, no Dogecoin jokes. But if you look at that top 25 list, I forget the exact number, I believe it's 7. Only 7 of those top 25 buckets of problems in your software that can lead to exploits by criminals, by terrorist states. Only about 7 of those 25 have anything to do with memory safety. So yeah, we want to plug those, absolutely, but that's that one colored tank at the top right. We can't forget about all the others. We can't say, oh, like, okay, we did memory safety and now we're good and we can declare victory and go home. No, there's still many others. SQL injection, you didn't sanitize your inputs. Stealing credentials that are posted in a public GitHub repo. I wish I was making that up. I am not making that up. Kubernetes vulnerabilities, all sorts of network attacks that are unrelated to the memory safety of the programming language. If we want to harden our civilization, we had better go and fix those too. But because we're here talking about programming languages, and C++ wants to focus on those main 7 ones, for example, I'm going to focus on those, but remember those are not the only places where our software is at risk. If we do a perfect job on that, we are not done as a society. There's still more work to do, but let's do our part of the job in programming languages. So the metaphor I use here is of a kitchen. We have a C++ as a programming language. Every programming language is an expert tool to varying degrees, right? Especially C++ is an expert language. The joke is if you want to take a sharp knife, one of those sharp knives that C++ programmers use away from a C++ programmer, good luck. You will not be able to take a sharp knife away. The ability to reinterpret cast when they need to use a raw union for type punning when they need to eliminate a bounds check when they need to in performance-sensitive code. But the problem is that right now, just like a Michelin-trained chef needs the sharp knives, the problem is they're strewn around the kitchen haphazardly on the ground. It is possible to write safe software in C++ today, way easier than in C, because it has more abstraction and more safety by default. But it still gives you performance and control by default, and the safety is always available. If you're careful, you can write a safe C++ program. However, you can also easily write a line of code that you didn't realize has undefined behavior, and you compile it, and it compiles silently and appears to run, and you don't realize that you actually have a safety bug there. So that's like leaving your knives lying around the floor. It's very easy to accidentally slice your foot fairly regularly. So what we're proposing to do is to evolve C++ where we have the same knives because nobody's taken our important knives away. We need to be able to cook and make Michelin quality food. But let's just put them in drawers. So they're still in the kitchen, same chef, but I just have to open the drawer when I want to use the knife. So if I want to use a reinterpret cast, I'll opt into that in the code saying like suppress the type profile, for example, or something, to be able to say, okay, now I really meant it. Now I can use the reinterpret cast. It's very much like the other safe languages have keywords like unsafe. And so, okay, in this block, allow me to do some more unsafe things. We need something like that in C++. And because we have a lot of unsafe things, we probably want more than one drawer and to be able to label them. So we can say which unsafety, which drawer, which kind of tool do we want to use in this line of code. So when you look at those vulnerabilities, the safety issues are in 4 major areas. All of the 7 of those top 25 that I mentioned that are about programming language vulnerabilities are about type safety, bound safety, initialization safety, and lifetime safety. So, and the biggest by far is bounds. Like in the top 7, 2 of them are out of bounds read and out of bounds write. This is obviously the low-hanging fruit we need to do something about. And so we've already been doing things in the standard to have key safe libraries like span, which is better than a raw pointer. It's because it knows its bounds. It can point to an area of contiguous things, use the span instead of pointer arithmetic. Safety-related undefined behavior is being removed, so I'm going to give an example of that, and talk about profiles and contracts a little bit as things we're working on to try to continue improving things. But let me give you some examples. So undefined behavior in C++ basically means the compiler can translate your code to do anything. The usual example is send a missile to the Soviet Union. You can see how old that example is, right? And so, but also time travel optimizations that change code before, create impossible values in your debugger, things like that. So C++ 26 has introduced already For the first time in like 30 years, we've introduced a new kind of error between undefined and implementation defined and fully defined. There's another kind, which is erroneous behavior. And this is basically saying this is code that we know we let you write, but it is wrong and we're going to treat it as wrong. In fact, we may, at this instruction or soon thereafter, at the point where you do erroneous behavior, we may terminate your process, which is what the default you want for safety. But the key thing is, even if you continue, it's not undefined, which means you don't get things like time travel optimizations and leaking secrets. And I'll give an example now of leaking secrets. Because the first place where we applied this new tool was to uninitialize local variables. Now I'm curious, how many of you know that in C and in C++, if you write in the body of a function, if you write an int variable on the stack by saying int x semicolon, how many of you know that that variable x is not initialized? So what value does it have? Don't know. It may have, typically in practice, it has the value of whatever the memory was before because we didn't actually write to it. So you can read whatever was there before. Wait for it, I'm about to show you. But technically it's undefined behavior. Your program could actually crash. For example, if the compiler made assumptions about the value of that variable and then optimized your function based on that. So you could actually do worse. You could actually crash or get other corruption. But most of the time, you'll just see some random value. In C++ 26, just by recompiling your code with a new C++ 26 compiler, which we're about to ship, and several implementations are already working on this, and I'll show you how you can use it today, before then, you're going to remove that class of vulnerabilities. You will not get undefined behavior for uninitialized local variables. Instead, you'll get erroneous behavior, which means you'll get some value, not necessarily a predictable one. It might be 0, it might be hex CD, it might be halt your program, but you're not going to get undefined behavior. And here's why that's important for safety and also for security. Notice here we have a function, f1, that has a character array on the stack. The examples can often be more complex than this. I'm just giving a very simple example so you can see what's going on. So this function, which notice in main we call first, puts a character array on the stack whose contents are, let's say, secret. Then it returns. So what happens when it returns here? Well, we just adjust the stack pointer, right? So whatever the stack frame that was, the memory for that invocation of the function for its locals and its parameters, we just change the stack pointer, but the stack memory is still sitting there. By default, it still has all the values that were there before, including secret, right? So now we call another function. Notice these functions are unrelated. They could come from different headers, different libraries, written by different people. Function F2 could have just been written yesterday, whereas function 1 was written 30 years ago. But now, if function 1 is executed and then function 2 has an uninitialized character array on the stack. And if you call a function that prints the contents of the array, today I say in the comment, this likely prints secret. In fact, on GCC, these are the 3 major C++ compilers. The first is GCC, then Clang, and then Microsoft. All 3 of them do, in fact, disclose that secret. So what do you do today? At the minimum, the first function, F1, first of all, why are you putting data on the stack? But if you must, then memset your stack, and then it turns out compilers like to optimize away a memset. So you have to be careful with how you memset it to make sure it really does memset, that you really clear out the data before you return. Or you can just recompile in C++ 26, and if you do that, you'll get something, but it won't be the original values. Just by recompiling in C++ 26, this code is safer. This code is more secure. And that's really important. And by the way, you'll notice on the right-hand side of the screen, I show the flags, the compiler flags you can actually use today, even before you get a C++ 26 compiler, because This feature is available on all the major compilers, but you have to use a switch to get the behavior. With C++ 26, it's just safer by default. Just recompile your code with a new compiler, and it's safer. And pause for a moment and consider this from a practical point of view. This is quantitatively better because we're eliminating a certain class of undefined behavior. So that's a good thing, right? But I want to point out qualitatively, as you, especially to those of you who are in academia right now, not in industry as much yet, when you're in industry, as you work on new products, whether it's a new app for a phone or a new version of an in-house software product or library that's used by other teams in your organization, anytime you do a new thing, it's super important to think about adoptability. Super important. Like, how hard is it to use your shiny new thing? Because, I mean, you have a selling job to do anyway, right? You got to go around and tell people, look, here's my shiny new thing. Here's why I hope you love it. It's beautiful. See, it does this. It's an app that lets you play this great bubble game or something, right? You have to convince them why it's better. It's this library that is better because it has these options or whatever. Great. But if they go to the App Store and the download link doesn't work, or it takes 3 days to download, or it requires a subscription, or you have a new library, but it requires you to have all your libraries, all the other 100 libraries you use, be updated before you can start using that one. These are things we call adoption barriers. They add friction, is another way we colloquially say it, to adopting the new thing, whether it's a library or an app or a device or any new streaming service, whatever it is. Don't get me started in the US about HBO Max. It was notoriously the hardest one to get started with. It was almost like they didn't want you to use their service. Netflix, they know about adoptability and making it easier for you to get started. So qualitatively, I want to point out this thing I just said very quickly of just take your existing C++ code, recompile it without change. Recompile it with a C++ 26 compiler, and it's safer. This is the holy grail of adoption stories. All I had to do was download a new compiler and recompile my code. You are eventually someday going to be in the situation, if you aren't already, where you want to adopt a new compiler or a new library that requires changes to your code before you can adopt it, or a new static analysis tool or something. And you are going to have a fun conversation with your manager, their manager, and your executive vice president about, yeah, I know it's going to take us 2 weeks of time to update the code so we can use the new thing. How many of you have gone through this? Show of hands? Yeah. And those of you, when you enter industry, more of you will. And you know what that executive is going to say about half the time? I'm being very optimistic here. It's probably more. They'll say, 2 weeks? Yeah, well, that's important. I believe you will do that, next year, because right now we have features that we need to ship. So we'll get to that. Maybe they do, maybe they don't. But that's an adoption cost. It's an adoption blocker. So I am super thrilled to see what the committee is doing here, because it shows an awareness of delivering safety in ways that are easy to adopt, that people will actually use. Because you know what? If you build that new phone that's way better than an iPhone and nobody ever uses it because it's just too hard or too expensive, you've built a beautiful device that you can put in your hallway trophy case that will have no impact on the world, that only you can admire and think about what could have been. What matters, value comes not from the value that's inherent in the product alone, it's value that's used, that people actually have in their hands, on their desktops, that is deployed in practice. And this is the kind of adoption story you want. So one question I sometimes get is, well, what about, you just talked about undefined behavior, so what about undefined behavior in C++? Could C++ really evolve to get rid of most safety-related undefined behavior? And now let me set some guardrails here, because some things are going to be very hard. Like, for example, dangling pointers are not things we can detect locally, and so those will be very hard. But you'll know that most of the CWEs I talked about are things like out of bounds read, out of bounds write, type punning, that kind of thing. So let me now take a poll with the caveat that a few things will be hard, like dangling pointers, and we're going to work on those too, but a few things will be hard. How many of you, by show of hands, think it's believable? Would you believe me if I told you that C++ could evolve to eliminate most safety-related undefined behavior? How many of you would believe me because I look pretty trustworthy? Which I hope I do. Oh, more hands went up, so maybe you agree, or you're being kind. Okay. So a minority of you. So first of all, thanks for the people who put up their hands. Second, congratulations to the people who didn't just believe it because I say so. Ask for evidence, right? I know this is an uphill job to convince you. Let me try to point out a couple of things that may help convince you. And I may or may not take that poll again afterwards. We'll see how good of a salesman I am here. Remember we talked about compile time programming, like reflection, const eval, generating code? That was part one of the talk. And you might have said, oh, wait, oh yeah, that was so long ago. That was some other unrelated topic. Wait for it. I told you they were related. This is the slide I was talking about. Now we talked about safety. We talked about safety profiles, checks, guarantees that we might have. This is a Venn diagram. You know, one of the things in the overlap here? Both of them involve less undefined behavior. Huh? Wait. What? Because, okay, you might believe me on the right-hand side. How many of you believe me, and I hope every hand goes up, hint, that having more language safety requires less undefined behavior, right? Okay, like that's better, right? If we don't have less undefined behavior, like we haven't done anything very interesting. Compile time programming, how many of you are not surprised to hear that compile time programming means less undefined behavior? A smaller, that's more than I expected. Why? Anybody want to shout it out since there are so many of you? Why? Who said that? Wave. You can't have undefined behavior in const eval. Are you on the committee? No. Wow, we're doing a better job educating than I thought. How many of you knew that in const expr code, and so const eval is const expr code that is guaranteed to must run at compile time, const expr code that does run at compile time, how many of you know we already ban undefined behavior, all undefined behavior in that code? Not too many. Yes, this is actually already true. Remember I told you that C++ is already using more and more and more const expr and const eval code. We're running more and more C++ at compile time. That code, when run at compile time, has no undefined behavior. The compiler is required to check it and diagnose undefined behavior. So we already have. So hold on to your hats, because most people are surprised by this statement, but let me say it in this way that's really shocking perhaps. We already have a dialect of C++ that has zero undefined behavior. It is C++ code run at compile time, const expr code when run at compile time, and const eval code. Here's an example. Here's your factorial function. I did the screenshot. I updated this just earlier today on Godbolt to make it a little more readable. I like auto, so sue me. And the factorial function takes a number, does the loop to multiply by the number. We all know what a factorial is. We're all high school graduates. And then main assigns the call factorial 13, assigns that value to a const expr local, which requires the computation to be done at compile time. So that's that last const expr on line 11 requires that whole computation, that execution of the factorial function to be done at compile time. But by the way, how many of you can guess how you could run C++ code at compile time? What do you need? Anyone want to say a keyword? Or a key word or phrase? Godbolt. No, you do not. Well, I mean, Godbolt will do it too, but what do you need in the C++ compiler? An interpreter. Who said interpreter? Raise your hand, yes. Once we started adding context to the language, we essentially required every C++ compiler to also contain a C++ interpreter. That interpreter is free of undefined behavior. And now, nearly the whole language can be run in that interpreter. So here, it turns out that factorial of 13, at least on a 32-bit system, factorial of 13 is, let's just say, too big. So notice that we have red squiggles here, because this is Godbolt. Thank you, Nathan. And if you look at, on the top, GCC, in the middle, Clang, and on the bottom, Microsoft's compiler, MSVC, all of them diagnose this as a hard error. Now notice what's going on here. That line, 5, is just doing a multiplication, but what does it do? The multiplication does integer overflow. And that overflow is currently undefined behavior. It could summon nasal demons, format your hard drive, all those things. But all of them say, look, at GCC I like, it says, look, this expression, ret times equals n, overflowing constant expression. Okay, it's giving you some information. By the way, this is a great reason to run your code against more than one compiler. If you don't understand the error message in one compiler, try, like seriously, we do this all the time, right? Run it under another compiler. So if you want to know more about this, try Clang, and Clang actually tells you what the value is. And if you notice down here near the bottom, it says, I got all the way down to 3, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, and then I overflowed. It'll even tell you which nested iteration overflowed. And Microsoft's compiler also says, hey, look, it's actually signed overflow because unsigned overflow is not UB. So it's actually signed overflow caused by the multiplication operation in some invocation of factorial, in this case, factorial int. So there's an example. But now let me show you something else. I just made this slide new today because this is something that most people don't know, even some standards committee members, because I'm so sorry. I have to admit, I learned about this about a week ago. So now you can say, I don't know a lot about C++, and especially you standards committee members, like Nathan, feel free. This function, bad bunny, not a diss against any musician, but you know, if you have a bad function, why not name it something youthful? So Bad Bunny, who I think no longer hates the Grammys, was that what the beef was? Or was it the Oscars? I forget. Has a local integer and then returns what? A reference to the local. So this is a bug, right? What's the bug? Lifetime, we have a dangling reference, same as dangling pointer. Why? Because we return and that storage is immediately freed and we're returning a reference to deallocated storage. If that was to a type with the destructor would have run. This is terrible, right? Well, I have good news for you. Even in C++20 mode, and probably back to mostly C++11 mode, I didn't check, compilers already all had warnings for this. GCC, Clang, and MSVC all had warnings for this. Anybody here, including committee members, want to tell me what this example does in C++23? Hands? Anybody? And I hope no hands come up, because then I'll feel less stupid for having only discovered this a week ago. Anybody? Committee members? I'm looking at a couple of faces I know. In C++23 mode, that is a hard error in portable standard C++. And GCC and Clang have already implemented that. So you'll still get a warning in all compilers that haven't been updated yet, and in older compilers. But this is a hard error already. This is another area where we've hardened the language because we know that if return of a local, it treats the local as what we call an expiring value. And it says, you know what? No more of that. You've been doing that for 30 years. It's time for you to break the habit. You're going clean, you're going to rehab. And our rehab is called error cannot bind non-const L value reference of type int ref to an R value of type int. Most people did not know C++ is already evolving to be safer. This is a common gotcha. When people complain about C++, this is an example they cite all the time about look how bad C++ is, and they didn't notice we already fixed it. Because they've tried it and been burned so many times, you just assume it's there. That's more undefined behavior that is denied by default in C++ 23 already. And so our approach is we have erroneous behavior, which I've already talked about. We have contracts and profiles. So contracts are like preconditions and assert in the language that is better than a macro assert from C. Is that a pretty good description, Nathan? Because he's a contracts guy. And so I want to make sure I sell it right for Nathan. Okay. And a profile, if you're familiar with a warning family, the way I usually explain it is a profile is like a warning family. It's a name for a group of warnings that we're going to treat as errors if the profile is enforced, like don't use static cast if you enforce the type safety profile, that kind of thing. Profiles are real new. We talked about them a lot at this meeting. We're still working on what the path is to get them to the standards. We're working on it, but people are encouraged about them, and we're trying to make sure the specification is correct and improve it. But there's a lot of support for that direction. We want to make sure we get the details right. Those three things together are going to help us deal with undefined behavior. And the way I look at it personally, now this is my slide, this is not the committee's slide, but the way I think about it, and other committee members will disagree with this, because I'm advertising this as my personal view, is profiles give you a name for a group of things, but they don't replace erroneous behavior. They don't replace contracts. They're better together. In fact, being able to give a name for a group of things applies also to runtime contract checks, applies also to a bunch of erroneous behavior that maybe is too expensive to turn on by default in the language, but I want to make it easy to opt into, so I give it a nice, easy name, right? But these are all just tools that I hope that we will do a lot toward systematically addressing undefined behavior in runtime C++, just as we've already done in compile time C++. Finally, let me talk about how each of these, reflection and safety, will help us with simplicity. And when I say simplicity, remember, I'm talking about two kinds of simplicity. First, the code you write. So how simple is my code and clear? And I mean, simpler code is easier to get correct. It's more fun to write. It takes less time to write. It's easier for ChatGPT to write. All those things. And how does it make my tool chains simpler? So I can get a bit closer to the, just install my compiler and compile and I've got the result, and I need less apparatus. You're always going to need some apparatus. I'm not selling you snake oil. I'm not selling you that you're going to live in a world where you just push one button and everything is perfect. But we can simplify the complexity in the language and in our tooling that we have today. So let's first talk about reflection and how reflection helps simplicity. So one of the proposals that comes from me, but is now really just a little tiny syntactic sugar on top of reflection now that we have it, or are about to have it, is I've been proposing that we take this idiom that we'll be able to write soon in C++ 26 and a little bit more, hopefully, and give it a short syntax. So let's first see what this is doing. It's saying, the first line says, I'm going to write a class widget. Notice that part is not highlighted. I'm just writing a normal class widget, but I'm going to wrap it in a prototype namespace. So it's not in this current namespace. I'm going to put it in a sub namespace. Why? Because I'm now going to run a meta function. Call it metafunc. It could be some meaningful name. It's just some function name, some compile time function that takes hat, that's the reflection of prototype widget. And what that meta function does when I run it is it creates a class widget here that applies some defaults and rules from the prototype widget that I wrote. And one of the things this lets me do is I can have an easier time writing a much simpler code for prototype widget and let the meta function fill in more details for me. And I'll give you an example. But I'm proposing that we have a shorthand syntax, and this is the syntax that the committee has encouraged for this feature. It's not part of C++26, but has been encouraged by the committee to say, hey, I'm not just writing any kind of class, I'm writing a class to which you should apply this meta function and have that be syntactic sugar for the above. Let me show you how that can be used. The simplest example, this is not limited to OO and virtual functions and inheritance and all that, but it's a simple thing to talk about because Java and C# and many languages have the idea of interfaces, right? How many of you have used Java or C#? Okay, I guess we now know what language is taught at the school. So one of the things in Java and C# is you have class, but you also have interface, which is a different kind of type. It's like in the type system, it's a different thing from classes. And those just have pure virtual functions, basically. And then classes can implement them, i.e. inherit from them and such. In C++, we can write those today. We tend to call them abstract base classes, but they are interfaces. And we just write all that stuff on the left-hand side where we have class ifoo is an interface we name foo. And it has a function named f that returns an int and a function g that takes a stood string. But we want those two functions to be pure virtual. So we have to write virtual before and equals 0 afterwards. Don't ask me why, long story. And we really ought to be writing a pure virtual destructor. If we didn't, our linter tool hopefully will complain because we want polymorphic deletion too. Otherwise, we might get an error there with destruction. Oh, and we also want to have a default constructor which gets suppressed when we delete the copy and assignment operators, because for an interface, it's all about virtual functions, and usually you would have a clone function that goes deep to the actual derived type and copies it and returns you back a pointer to the interface. You don't have just a shallow copy construction. You usually suppress those because shallow copy construction, copy assignment isn't what you want, so you suppress them. C# Java programmers look at that and say, sucks to be you. Because you had to write all that stuff, and in C# and Java, what do you write? Interface, ifoo, brace, int, f paren, semicolon, void, g, string, semicolon, close brace, and you don't even have to write that last semicolon, right? We're such better languages, right? Wait for it, because with reflection and with that super tiny but really useful convenient syntax that I've proposed for the standard and the reflection proposal that many other people have worked on, you will be able to simply write class paren interface paren ifoo, and I can show you in detail how this works. We'll cut the details for time, but look at my paper, look at my on GitHub, my CPP front implementation in a syntactic dialect of C++, but it compiles straight to C++ to see this and many meta functions. All it does, spoiler alert, you ready for a spoiler? Interface is just a const eval function. Just ordinary C++ function that does, drumroll, reflection. This syntax just says, remember what we said on the previous slide? Reflect on the body, the name and the body of the type that the user actually wrote, and generate a variant, something that's based on that, but could fill in defaults, could generate functions for you. Because the way to think about this is I could put any metafunction name there, and the metafunction now gives me a word of power. It says, oh, this is a compile time function that takes a reflection of a class and does generation right here in this current namespace of another class, in this case with the same name, but with additional members and changes to the original data, the original member functions. But it's just a name, in this case, interface. Interface is a meta function which enumerates over four, remember that for loop, for every member function? Generate one that's the same name, same signature, but is virtual equals 0, pure virtual. Oh, by the way, always insert a virtual destructor. Always insert a default constructor. Always delete copy. The right-hand side generates the left-hand side. And I can do this with any kind of type. And the way to think about this is now when I'm writing a type, if I just say class something, open brace, Oh, what kind of class am I writing? I don't know. I have to remember what the one-size-fits-all language defaults are in C++. Maybe I'm writing a copy of a class, but maybe I'm not. Maybe it's an interface, maybe it's a trait, maybe it's a functor. There's all sorts of things I could be writing. Here, now I can say, I am writing a class, but not just any class. I'm declaring declaratively up front, I am writing an interface. And I get all of that done for me. And in previous talks, you can find them on YouTube, I have shown with live demos that you get the same usability, the same error messages as in C# without having had to put a separate interface concept into the language. And this implementation is about 10 lines of code, of real C++ code that is running at compile time, whereas the C# implementation of interface is a whole new type. They have to plumb through their whole language specification. It's about 12 pages that a compiler has to implement. That is an example of the power of reflection and generation and how it is a game changer. Because I'm going to tell you right now, this is one of those examples that separate C++ 20, this was probably 29 code from what came before. Because where you will be able to open up and see in almost any 10 lines of code, you see class paren, because you'll be seeing this a lot. You'll be using this all the time when you define your types, because it'll be so convenient. For virtually every type you ever write in the future, you'll know you're dealing with modern C++, not C++ 11 and that first of modern iteration. It's that much of a game changer. But it also helps with simplifier tools because, for example, how many of you have used Qt? Oh, wow. Cool. I don't know if they use it here or have used it in industry. It's certainly popular. You write the stuff on the left-hand side with macros and everything. And what you'll be able to do with reflection is to write class. I'm not writing any type of class. I'm writing a Qt class. And get much simpler direct expression of intent without this machinery of getters and setters and signals and slots with its own syntax. But it's not just the syntax. Remember I told you that in this next decade of C++, not only will our code be simpler, remember I said our tools will be simpler? So those of you who put your hands up for Qt, how many of you know or can say in a few words, how does all that code on the left actually get compiled? Shout it out. Meta Object Compiler, also known as the mock compiler, MOC, which takes, in this case, because it needs more information than I can put in the C++ code today, so you need language extensions, some of them macros, and you need a separate compiler that in this case takes an extended version of your C++ source file, reads that extra stuff, strips it out, so that then the C++ compiler doesn't have to see it, compiles some generated code from that, and your C++ file through a C++ compiler. One of our hopes is, and I'm not making any product announcements for Qt, but I know that Qt are watching this feature specifically because if it works as advertised in the coming years or decade, it could let them get rid of having to support a separate meta object compiler and just compile with C++. Remember I was talking about simplifying your tool chains where you can get closer to being able to just take your code, run it through a C++ compiler and run the executable? I mean, you'll still need a package manager and you'll still need other stuff. I'm not claiming it's going to be nothing, but that's a simplification right there. That is a simplification. For you as a user, because you don't have to configure and run the mock compiler, and for whoever is maintaining and supporting your mock compiler, because it's a cost for them too. Supporting a whole compiler is not free. There is cost and complexity to doing that, fixing bugs, staying compatible with C++ as it evolves, right? So there's a big carrot, a big incentive for you as users, but also for the purveyors of these side compilers to see, when could it make sense to simplify this? And so we can stop maintaining that tool. Same thing for COM. I won't go into the details, but if you've done COM style programming in C++, you have to have this idle file that either The idle extensions either are inside the same file and it runs in an extended C++ compiler, which is not portable, or it runs in a side compiler, an idle compiler or a middle compiler, and this is the complexity of your tool chain. This is what you do today to write Windows Store apps, for example. We'd like to get to the right-hand side. Now notice I've been saying these slides are from my talk in 2017, is the first time I talked publicly about this vision. And I have gotten flack occasionally over time, including from a few committee members saying, so how's metaclasses going? And I say, it's actually going pretty well. Reflection is gradually progressing, and 95% of my paper was reflection and motivating why, please, let's have reflection. At my first committee meeting where I showed this paper, I actually came after, it was Toronto, remember Toronto, Nathan? One of the Toronto meetings. And I came in 2017, summer. It was hot. And it was at the University of Toronto, I believe. And I came right after the reflection presentation. I think it was David who gave that presentation. I can't recall which reflection proposal it was then. And the first words, when it was my turn, they said, okay, Herb, show your paper. My first words to that committee subgroup was, hi, my name is Herb, and I'm their customer. Because I want to build on everything they're doing. I need reflection so bad. If you give me reflection, I can do this. You can do this. And so now we are in a place where reflection is landing, and I just want my two-line syntactic sugar, and then we can open up together this kind of world. By the way, this isn't just big companies like Microsoft and Qt that do this. I immediately got email from Axel Naumann at CERN, who said, oh yeah, we have this YAML script where in YAML we say what the basic, here's a type, it has certain attributes and certain members, and then we generate 5 interrelated classes that know about each other, but are derived from those data members and are connected in certain ways. They'll be able to simply write a meta function and stop running a separate YAML compiler, which is what they do today, to run just in C++. Now, I gave these slides as a reminder. Remember what we talked about 7 years ago? This was in my September talk of last year at CPPCon. I reminded people of this. That's the first time I gave this talk in public. And I reminded people of this. And I showed them these slides, these 4 slides. And I got to tell you what happened, because it's a funny story. We have time, right? So, you're working on your talk. And you can't enjoy the conference until your talk is done, right? Because you can't stop thinking about your talk. And I'm seeing nodded people going, yeah. It's like, okay, so anybody who's given a talk, you've been there. Same thing as if you're writing a paper before you submit it to the professor, right? You're working on it to the last minute. And then you're all nervous and you give the talk or you submit the paper to your prof. And then whatever happened, right? It's too late now to worry about it. So you go have a beer, right? So you relax because whatever happened. Now I can enjoy the rest of the conference or I can enjoy my next class. I pulled my all-nighter, maybe now I get some sleep, right? That kind of thing. So I went back to my room. When I'd recovered, a little while later, I decided, I'm thirsty, I need some coffee. So I got ready, opened my room door, stepped out, closed the hotel room door, and I started walking down to the elevator. And about halfway to the elevator, somebody else was going the other way and who was wearing a conference badge, saw me, turned around and started walking with me. This happens from time to time. And he said, hey, that talk you gave, and you know how you showed all these different side compilers? At my company, we actually have a side compiler where we generate C++ from a script. And if we had reflection, that's exactly what we would need. We could stop supporting that compiler because it's a pain to support it and maintain it and update it. This is great. So thank you for the talk. I hope this comes soon. Great. So we're walking along. Can you see where this is going? We get on the elevator. Ding. We get on. Ding. Elevator starts going down. I think I was on the 9th floor or something like that. About halfway down, ding, someone else wants to get on around the 4th or 5th floor. So we make room. Another person comes in. They're also wearing a conference badge. I don't know him. He doesn't know him. He looks and says, hey, I enjoyed your talk. You know what? On my team at home, we have a side compiler, a middle code generator that generates the C++ code. And if we had reflection and generation, we wouldn't have to maintain that thing anymore, which is such a pain for us. And now I've learned from this that at this point is the right time for me to say, could I have a show of hands? How many of you currently or have worked in an environment that have such an internal compiler or script that generates C++? How many? A good number, and that's with like half of you being students. This is a popular indoor sport. Do not tell me for a moment that people aren't going to be aching to adopt C++26, C++29, and onward. If people are not convinced, they will be convinced once you show them it makes your code simpler, it makes your toolchain simpler. It's a big deal. So welcome to C++'s next decade. Now, we're just getting started. One of the problems I have when I give talks like this, remember, we kind of, at the committee, we live in the future, right? In that we're thinking about C++26, and I know some of you may be thinking, Herb, have you checked the calendar? It just got to be 2025. Did you miss New Year's? Like what? Like you keep saying C++26. I don't graduate for another. That's not going to be available till I graduate. That's so far away. So first of all, it's not. So I have to apologize, though, that we are living in the future and we're talking about things that you often can't use today, although I showed you some switches you can do to eliminate your uninitialized stack variables that you can use today already. But compilers are not waiting to implement C++26. Because we ship regularly every 3 years and we're predictable, we have built up credibility with compiler vendors. They can trust us to know that we ship regularly at high quality. This is a big deal. It's a lot of work, but thank you to everyone in the committee to make it possible that we do that. And that is why, instead of the old days 20 years ago, where we would ship a standard and then 3 to 5 years later, compilers would be up to date in implementing all of it. That's what it took. It is normal now. It is normal for us to ship a standard and for there to be at least one of the major implementations already fully conforming, modulo bugs as always, software has bugs, but modulo bugs, to have implemented all the features the same year the standard is published. Why? Because they didn't wait for the ink to dry. And as we stand here today, it is February 2025. We're not going to finalize the standard for about another 13 months. Then it's got to go through international ballot and review. At best, at the end of 2026, which is almost 2 years from now, the standard will be published, right? But this is the week for the feature freeze. And as I stand here today, Clang and GCC already implement 2/3 of C++26 features. So when we talk about C++26, do not make the mistake of thinking of it as some abstract future thing. It is true that many of the things I'm talking about, including reflection, which has not merged yet, and if it's going to make it, we hope it merges in Bulgaria. Feature freezes now, but it's already been approved. The wording freeze, the specification freeze, is in Bulgaria in June. It hasn't entered the standard yet, so that part hasn't been implemented in major compilers trunks yet. But they can see it coming. And they've implemented all the stuff that we've been building over the last 2 years already aggressively. So 2/3 of that, of C++26 that we've approved already exists in GCC and Clang. So don't think of this as some far future thing. But reflection and generation, I believe, are going to dominate the next decade of C++. In being able to generate Rust wrappers just automatically from C++ code as .rust files or .java files for Java wrappers, for being able to have metaclasses to declare your intent so your code is ever so much more concise and you get exactly the right defaults because you said what kind of class you're writing, without bifurcating the type system as just ordinary C++ run at compile time. And that will make easier some things that we can do today, but they're kind of verbose and icky and error prone, like template metaprogramming, expression templates, and make possible things that are really infeasible today, where today we build a side compiler. So I remember when I gave those 4 examples, 2 of them were COM, and 1 of them was C++CX. So I led the design team of C++CX. And I did that as proprietary Microsoft extensions to the language, not because Microsoft loves being proprietary and locking you in. I do not speak for everyone, but that was not my experience while I was there. It is not because I hated standard C++ and wanted to do something different. It's because I had to. We felt we had to, because C++ was not yet expressive enough to express all the things we needed to do in C++ CX, and the same thing earlier for C++ CLI, which I also led. And my goal with this metaclasses proposal and pushing reflection is I've been down this road at least twice with C++ CLI, C++ CX. I've helped build and maintain those side compilers. And I don't want to design that anymore, and I'm pretty sure I know what the requirements are because I led 2 of those design teams. And I never want to do that again. I want to be able to do that in standard portable C++, and I'm so excited that it's getting real. It's so achingly close to getting real. You have to cut me a little slack. When you work in standardization, you need a ton of patience. Reflection proposals have started being proposed in this committee 21 years ago. I started proposing metaclasses, the stuff I just showed you on the screen that now I can show you working on Godbolt, but I couldn't then. I started proposing that 7.5 years ago. You need to be patient because things can take time to bake. But remember, we're not just saying, hey, let's check in a random feature and see if it works. We're making changes to an international standard where once you put it in, it is cast in stinking stone. And you do not get to take a breaking change to that. You're going to maintain that for the next 20 years. So you better have pretty high confidence that this is going to be durable, that this is going to work. And sometimes we get it wrong because we do try to be aggressive. But for the bigger features, it takes time to bake and get it right. But it can be frustrating. It can say, but wait, I wasn't even planning to be in this career for that long. Well, and most features don't take 20 years, but they may take, some of the smaller features may take 2 years or 3 years of your life to get in. Not full time, but you need to, with that amount of coming to meetings and iteratively improving them. But here's the payoff. Are you ready? Once you do it, you have turned a supertanker. It takes a lot of effort to turn a supertanker. But once you've turned it, you've got a bazillion barrels of oil going a different direction, and you've changed the course of how that programming language is going to influence not just a few people, but about 10 million or so programmers who use C++. Numbers are hard to come by. The most recent things I've heard about are around 8 and 10. It depends who you ask and how you count. I won't make jokes about how much personal identifiable information you collect surreptitiously, because that's totally a joke. They don't do that as far as I know. But it is hard to count. You basically go on Stack Overflow surveys and things like that. But once you've done the work, you've delivered a feature, maybe it's the override specifier in virtual functions, something pretty small, right? Yeah, but now millions of people get to use that. And the impact of what you have delivered has an outsized impact. It's like being at a leverage point in the world. That means there's responsibility on you. You better get it right. Don't go guessing. Sometimes we do guess. We're all human. We're all imperfect. We'll make mistakes. We'll realize 20 years later, oh, we could have done it better if only we'd known what we have now. You know what? None of us is as smart as our future self. Don't beat yourself up over it. Do the best job you can now responsibly by gathering the data you can. But sometimes 10 years, 20 years later, you will have a conversation of the form, if I had a time machine. Those are actual words spoken at almost every committee meeting. It's like, if we had a time machine and we could make this change, but we can't do it now because it would break the world. We've already gone down a different path, right? But you have outsized impact. So there's high responsibility, but also high benefit. Finally, let's talk about the importance of safety. So one of the things that I hope to convince the committee in the next couple of years, I have not convinced them yet, but I've implemented them in my CPP front compiler, is to say, hey, can we automatically take every A sub B subscript expression and just check it? We know by doing a quick lookup whether it's a container that supports std size of A. We know whether B is an integral type, in which case we can just inject a call site bounds check for that. And I have done this in my CPP front compiler, which works with all existing C++ code. And when you do the call, so it works with the standard library, with Qt and such. In CPP2 code, my alternate syntax, C++ syntax, when you use a std vector, a std range, a Qt array, anything like that that's indexable, you just get bounds checking. It just works, and it's great. I just found another bounds check last week before I came to the committee meeting. I was writing some new reflection code, and this time it was actually a non-obvious bug. It wasn't just off by one. I was subscripting over a different container than I thought I was. So I knew the right bounds, but I was calling a different container. It can happen to all of us, but I was working in a future-ish, an experimental version of C++ with a slightly different syntax where that was automatically checked. And I hope to propose that again for a post C++ 26 for the standard, perhaps under a profile. We'll see how that goes, because you got to convince people. Remember, when I was introduced as the boss, that is the wrong word. I'm just one of many people making proposals, and I got to have the same burden to convince people that I'm not smoking something illegal when I was writing that paper, and that it actually works. And they will point out real problems with my papers. My papers are imperfect. They will point out real problems that need to be improved. It's a humbling process. And let me tell you, the committee members are not shy to tell you where your mistakes are. Would you agree with that? Is that your experience too, Nathan? Yes. But this works great. So I have a convincing job to do, but it works great. And now I get out of the box. If we had this in, say, C++ 29, it would mean that I could recompile my code with a C++ 29 compiler. And for all my standard arrays and spans and ranges, and my Qt containers, which overload std size and things like that, I just get bounds checking out of the box, opt in, and I can opt out of the overhead when I want to. That's that nice seamless adoption experience I was talking about before. So here's an example that works today in my CPP front compiler. Briefly, uncomment one of those first two lines. It doesn't matter whether it's a C array or a vector of int. If you print a sub 1, a sub 2, a sub 3, what's the problem? Off by one error, right? The arrays are zero based. It should have been 0, 1, 2, not 1, 2, 3. Yeah, bad programmer. If you run that through my compiler that transpiles this to C++ and then run it on the Microsoft compiler, you will get bound safety violation, out of bounds access attempt detected. Notice it tells you the exact line number and source file it came from if the C++ 20 source location is available. And it tells you what the actual bounds were and what the index you tried to access was. And because my compiler runs before the C++ compiler and it works on any C++ compiler, you get the same thing in GCC, for example. And the syntax is slightly different because of what source location says, but demo CPP2 line 7, and you get the bound safety violation. So this is the kind of thing that we do not have yet in C++ 26. I still need to convince the committee to do something like this, but we are moving in this kind of direction. And that also is a change in C++. And I will tell you one specific way that I expect to be the litmus test on have we really done what feels like a new language, even though it's fully backward compatible, is can I take any random 10 lines, and let's be generous, 20 lines of code, and can I just tell that it's new versus old? I can do that with C++ 11 for sure. Like any random 10, 20 lines of code, if it's C++ 20 era code, I can pretty much tell, oh, it uses a unique pointer, that's a dead giveaway. Oh, a lambda, a range 4. Now I'll be able to say this is C++ 26 era in the decade code just by saying, does it use class paren to declare a type? Does it check its pointers for null before it dereferences? Because one of the things that I do in CPP2, which I hope to convince the committee of, and I love this so much, it cleans up your code remarkably. In my compiler itself, which is mostly still written in C++, parts are self-hosted in CPP2. I just religiously, my personal coding style is, even if I know a pointer must be null, I always assert it before a dereference in a function. So the first dereference in a function, I do assert, not null, and then I dereference it and use it. And even when you know it's not null, man, that has saved me many times. How many of you have the habit of writing assert p is not null before the first use of pointer p in a function? How many of you have that habit? Perfect. One of the things that I do in my my experimental syntax for C++, CPP2, is if you dereference a pointer, it always inserts a null check. Why does this change how you would see any random 10, 20 lines of code? Because if I convince the committee to do this in the future, then code that is written with that kind of check enabled wouldn't need those asserts. You could just look at it and know if it's compiled in that mode, it is correct. Now you have to make sure it's not compiled in a down-level mode where you're not doing a bad dereference. So we need to make sure that we handle that case of the code relies on it and is not compiled with a compiler that does the checks. But you can sure as heck tell that that is new era C++. Just like you can tell if it's class paren or whatever syntax the committee ends up agreeing. And again, some of these features are beyond C++ 26, but this is the era we're coming into because safety by default is not the norm today in C++. Your code is different when it's safe by default. It's visible in taking a look at 20 lines of code. So reflection and safety both are great features in themselves that have value for the world, but they're going to improve the simplicity of our code and of our tool chains. So that's why I'm excited. And as we peer forward to the next decade of C++, remember, I am an instance of class human. Therefore, I can be wrong. I'd lay pretty heavy odds on all the things I've told you today. And I am excited to see these things coming that I think will make C++ 26, 29 feel like a new language again because of the effects in particular, not just of great features like contracts and other things that we're getting, send to receiver for being able to do asynchronous and parallel programming, but specifically of safety by default and reflection will change the way we write our code for the better. It makes me very excited for the next decade to come. Any questions about any of that or other C++ things?
So let me thank her for taking us to on a tour to the near future of C++. Do you still have the power to ask some questions?
Yes, especially if they're in English. Ich würde es verstehen auf Deutsch, aber der technische Wortschatz ist nicht so gut. Nur ein Haushaltswortschatz. Yeah, so please say them in English because I do not have a very good German technical vocabulary. It is a household vocabulary. So English, please.
So then your questions, please.
Reflection stuff also sounds very much like you could do stuff like create JSON generator for your data class, right?
Exactly. Yes. One of the first things that people want to do, if you look at, so the idea of JSON serialization, there are in fact working examples of that in paper P2996. So again, wg21.link/P2996, you can find examples in the paper. But excellent, you're thinking exactly right. By the way, that's one of those things you want private reflection on private members for, which was a topic of that consumed quite a bit of Wednesday. So Tuesday, yes.
So my professional career is dominated by C++, I must say. I started programming 92. This was when C++ came up here in Hagenberg. And I'm still enjoying C++ all the years through. So thank you for your efforts.
Thank you for sticking with it. I'm glad it's useful for you.
There were some difficult years, I must say, from 2005 until 2011.
You too?
So yeah, probably this is one question. You probably felt similar. So this was like everything was evolving around in different languages, and C++ was kind of felt like stuck. Yeah, but yeah, since C++ 11, it's even more fun and more things to come. So one thing that's despite all the fun is compile times. Yeah, it always is like, I want to program test driven, all this, and then you feel I want to continue, and the compiler stops you. So what about compile times?
I'm glad you asked. Is what every politician says, whether they're about to answer or evade your answer, but I'm actually going to answer it. So I actually mean it. I'm glad you asked. That's an excellent question. So what about compile times? Herb, you just said we're doing more work at compile time. My compile times are already, are you crazy? Like, do you not know my pain? Wait for it. So when you replace, like we already do compile time programming in C++. We just do it by template metaprogramming and indirectly, things like that, right? We already, for example, run a separate mock compiler, a second compiler for COM and WinRT, right? When we are able to write the code in the C++ compiler, we can eliminate a whole nother compiler. When we replace template metaprogramming in C++, we replace template metaprogramming, the indirect expression of a computation, through a template type system that was never meant to do computation, but we're just abusing it for that because it's fun and we have to and we like sharp angle brackets. But you can replace that with compile time C++ itself, a context per function, way faster. Because it is way faster to interpret a context per function than to do template instantiation to indirectly compute through the type system some value as a side effect of a type computation. Oh my goodness. Why did we do template metaprogramming? Only because it was so useful and we had nothing better. I compare it to people digging with spoons. If you see people out there and they're busy in the yards digging with spoons, what does that tell you? I see a market for shovels. Right? Let me build you a shovel and a long handle. You don't have to bend over as far. You can get more for each scoop. So one of the things I pointed out is I have an example in a talk, I don't have it in this slide deck, where I show that compile time metafunction that's in my CPP front compiler, where a fellow actually from not too far from here, from Dresden, Uni Dresden, Max Sagebaum, he actually wrote a compile time regex function in my CPP2 syntax using reflection and generation. And when you compare it to the best, the world class, the current best in class C++ compile time regex, it has roughly the same feature set. The C++ compile time is about 2/3. So it's about 35% faster. But it's running a whole nother compiler, my CPP front compiler ahead of it. Like it's saving this much, and I'm not even making this up. Like this is how it looks on the slide. It's like from here to here. Here's the baseline. It goes down. It speeds up the CPP1, the current C++ compiler, this much because it's doing less template instantiation and context per and const eval, and it's doing like what looks like a line, not a bar, for the entire CPP front compilation to do reflection and generation. And here is why. You might say, well, why would that be? Like, why is context per functions that go through a whole C++ interpreter faster than template metaprogramming? Yes, you're running a whole other interpreter inside the C++ compiler, but it's because you directly expressed your intent. You didn't write an indirect program that is abusing something to get compute something that wasn't intended for computation, and you're doing it another way. You're using a const eval function to directly do that instead of abusing template instantiation. In the case of going from that to reflection and getting even more speed up, instead of actually running code through an interpreter, which I remember is already faster than the template metaprogramming, not only, and you're doing it now through reflection, my experience so far is because the reflection can generate the exact code you want. You don't have to run through the interpreter. So these actually are making compile times better. By the way, another thing that makes compile times better, they've been really slow to be deployed, but they're getting there in all the major implementations, is modules. Are you aware of C++ modules? Show of hands. One of the big advantages is compile time. So the entire standard library has, I don't know how many dozens of headers. It's got threads and async stuff and all sorts of fun things. Containers, iterators, ranges, all sorts of utilities. And so generally we try to pound include only the headers that we need, right? Because we're pasting in all this code through pound include, that increases compile time. When we have modules, a module basically pre-compiles the code that otherwise would be in the header. And it stores it all, but it stores it in a way that has basically an index in front and makes it very easy to do random access to load only the parts you refer to. This is so fast that as of C++23, there is one module for the entire standard library. Instead of like dozens of headers, there's one module, import std, semicolon. It is faster on all implementations, as far as I know. It's certainly on GCC and Microsoft. It is faster to module import the entire standard library and print hello world than to pound include just IOStream and print hello world. Hello world, importing the entire standard library is faster than hello world. So yes, we're paying attention to compile times, but I'm not minimizing it. I know they sure still are a pain point. But we're doing stuff. So my point is, I'm not invalidating what you say. You are right, there's still a bear. But there are real things happening that are making it better, including reflection will be faster, and especially than template metaprogramming. Let me take a couple more.
A question regarding getting rid of precompilers. So if I go back to your example on Qt to get rid of the meta object compiler, to get things like signals and slots working, I think you would need something like annotations of functions or there. Is there something in the proposal? Something like that?
So that's an excellent question. There are several ways you can do that. Let's go back to that example for a bit. Here we are. If I give you a problem statement, you're a smart programmer. You can think of several ways to write the code, right? A meta function is just code. So I'm going to give you the problem statement. I want to write a simpler version, something like the right-hand side, say, to say class, Q class. And you got to think of, okay, how will I have the information in the class that I can reflect on? How will I get enough information to know that this function should be a signal and this function should be a slot, say, right? Here is one answer, but it's not the only one. You can actually write this meta function several ways. Like one thing you could do is actually put an attribute signal or attribute slot, reflect for each function. If it has an attribute named signal, treat it as a signal, right? But that's a choice of your meta function. You could say, okay, to use my meta function in the place of Q class there, then annotate a signal or a slot as attributes on your functions. In this one, I'm doing something different. In this particular example, I'm just saying, as the QClass meta function goes for each member function in the class, so it's iterating for each non-static data as non-static member function in the class, if the return type starts with the word property, because I can ask what's the return type, I can turn that to a string, I can see if it has a certain name, then treat it as a property. Is the return type signal? That actually doesn't even have to be a type anywhere, right? It's just a word, because you're not actually compiling the code on the right, you're compiling what gets generated. So what you see in the code on the right is the input into the meta function. And in this case, I wrote the meta function, or I used the straw example of if the return type is the word signal, treat it as a signal. If the return type is the word slot, treat it as a slot. Now, If you need an actual type for the return type, then you can do what I did with property of int. But I just unwrap that. I just take the word property off and I use the int, and the int gets its get value and set value QProperty function. So do you see what I mean? You can actually do this several ways. You can have an annotation on each function. You can just read and look for special values or special names in the return types, and you can play around, because this is just code, and see what is easiest to use. You can do A/B testing to try one way and another on your users and get their feedback and see which they like better. It's just code. So there's several ways you could do that, but hopefully that gives you a flavor for what's possible. Really, it's up to you as the author of the meta function. You're going to reflect, and you decide where the information should be that you expect to get to use your meta function properly. Does that kind of answer your question in enough detail? Okay.
So I think we'll leave it with that. Thank you, Herb, again.
Vielen Dank. Thank you again.
Many thanks.
Und wiedermals vielen Dank, Uni Hagenberg, Software Park Hagenberg. It's been great.
You're welcome. Yes. And I also want to thank the audience for being here, and have a safe ride home.
And can I say one specific thank you? He did not know this is one of my favorites, okay? He did not know this. Thank you for the Linseltorte.
You're welcome.
Thank you. Have a good night. Thanks for coming.